Hi you guys, this is Mrs. McBride speaking, and I'm here to talk to you about thermochemistry. I wanted to talk to you about the word thermochemistry first. The word thermo actually means heat or energy, and of course you've got chemistry. So you've got thermochemistry is actually the study of heat or energy. Now, what exactly is energy? Energy is a capacity to do work or to produce heat. The law of conservation of energy states that energy can be neither created nor destroyed. That means that energy can simply transfer into another substance, but it can never be destroyed. The energy of the universe is always going to be constant. So since energy can not be destroyed, but rather it can be transferred, energy can be classified as potential energy or kinetic energy. Potential energy, you have learned in the past, is actually stored energy, but it is really the stored energy to do work or to move. And kinetic energy is the energy the energy of motion. So let's say that to illustrate to you the law of conservation of energy, or Loki, let's look at this model of a baseball that's being thrown in the air. You have the baseball in your hand, and as you have the baseball in your hand, it is not moving. Because it is not moving, the kinetic energy of the baseball is 0 joules. However, this baseball has a lot of stored energy. It has the potential to be moved. So the potential energy is at a max, or at a very high value. And as the ball is released from your hand and it goes up, now the kinetic energy is increasing and the potential energy is going down. So as the ball is moving up, now sooner or later the ball starts losing its motion and potential energy starts increasing until you get to the very top of the arc of the baseball throw. And when you get to the very top, now all of a sudden the potential energy is at a max. Because you may not be able to see it, but you certainly know that just for a split second, the ball has stopped. And when it does, it's got the potential to do work, so it's got a maximum potential energy. Because it isn't moving, the kinetic energy at this time is 0 joules. Now, as you're moving down, same thing is going to happen. Your kinetic energy is going to increase because now you're moving faster. The ball is moving faster and faster, and the potential energy is decreasing until you get to a point where now the kinetic energy starts decreasing and the potential energy is increasing to where the ball eventually comes to land somewhere where the potential energy is max, because it's got the potential to do work. It's stored energy to do work, but because it is not moving, the kinetic energy is 0 joules. Notice when I was telling you the scenario, that the scenario on the left-hand side of the ball moving up, the kinetic energy is moving up. And so the overall energy is going up, but on the other side, on the right-hand side, as the ball is moving down, you've got your energy that is moving down. But your kinetic energy and your potential energy are basically behaving the exact same on both sides. That's because both of these sides, the left side and the right side, are actually mirror images. The two energies are mirror imaging one another. They're increasing at about the same places and decreasing at the mirror image place. So this is actually related to the law of conservation of energy. And for short, we usually call it Loki. And what this means is that the potential energy and the kinetic energy, when you add them up together, they will equal 0 joules. Or basically, kinetic energy will equal the amount of the potential energy will equal the amount of the kinetic energy. So this is just relating to a baseball. But if I start talking about this as far as a chemical reaction goes, now if you look at this chemical reaction, A plus B yields C plus D. But what this is actually saying is that the energy in the reactant side actually equals the energy that's present in the product side. So essentially we can say that the energy of the reactant is equal to the energy of the product. And in this scenario, the energy overall is constant. It does not get created, nor does it get destroyed. The energy simply is transferred from one substance to the other. One of the things that we often look at when we talk about energy is temperature. And temperature is actually just it's just motions of particles, and they're completely random. So it's the random motion of particles. It's that's all the temperature is. As something, heat, on the other hand, is actually the transfer of energy. So the way you can actually detect what you can detect heat is through temperature differences, where if the molecules are moving really fast, they're going to have a high temperature. If the molecules are moving really slow, then the molecules will have actually have a lower temperature. So heat, on the other hand, the symbol for heat is Q, and the SI unit for heat is actually joules, capital J. Now let's talk about a chemical reaction. So in a chemical reaction, the place or the compound, the components that you're actually focusing on, that is called a system. Everything else around it is called surroundings. So the container, the room where the reaction is occurring, all of these are based on the surroundings that are surrounding the system. Never would you say that the reactant and the products are part of the surrounding, because that's really what usually you are looking at. So you wouldn't call the reactants and products part of the surroundings. Heat flow can be, there are two ways for heat to flow. And the two ways that heat flows is something called an exothermic and endothermic. The word exothermic, think of the word exo as an exit or outside, and this is when heat is actually released out. So heat is released, heat is lost. And this is actually denoted, since we're talking about heat flow, the symbol for heat is Q, we would say that we would give this a minus sign. The minus sign meaning that heat is flowing out of the system. On the other hand, you've got an endothermic reaction. The endo means in or inside, so the heat would be going back into the system, or it's being absorbed into the system. Of course, since we're talking about heat, we would say the symbol is Q. Of course, you can put a number value there, because usually we don't say Q, but rather we give you a number. This plus sign, on the other hand, indicates the direction where the heat is moving or flowing into, and if it's a positive sign, the heat is flowing back into the system, or the system is absorbing the heat. So you can basically see how both of these are equal to one another. The endothermic reaction is absorbing, exothermic is releasing. So they still are a part of this law of conservation of energy, where heat is moving from one place to another, not being destroyed, but simply being transferred. Now, if we move on to the next page in your notes, you can see that we've got this box here. The surroundings is the outside of the box, and inside, where we are talking about, that's part of your system. So if heat flows into the box, we would say that that's a plus Q. That's an endothermic reaction. And if heat, on the other hand, is flowing out of the box, we're saying that of the system, then we're saying that heat is being released, and that is a negative Q sign. It's an exothermic reaction. Now, clearly, once again, you can see how endothermic and exothermic, they're both equal to each other. And this is following the law of conservation of energy, where it's showing that it's constant. If heat flows into a system, it must have been lost somewhere else by another system. And so we're talking a lot about heat flow. This is actually a part of studying thermochemistry, where we talk about thermodynamics. Thermo, of course, means heat or energy again, but dynamics means motion. So we're actually talking about the motion of energy. And this really does bring us to the very first law of thermodynamics, which states that energy of the universe is constant. Once again, you don't lose it, you don't create energy, nor does it get destroyed. It simply is transferred from one substance to the other. And of course, energy, the unit for energy is joules, the SI unit, and it's a capital J. The last thing that I want to talk to you about is enthalpy. Now, enthalpy is denoted by the symbol capital H, and really enthalpy means energy flow. So if you have change in enthalpy, you'll have that triangle, and that simply means change in the energy flow, or the change in the heat flow. And that is denoted by this equation here. Change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. Now I'm going to talk more about enthalpy when I get to potential energy diagrams with you. But real quick, I wanted to recap that an endothermic reaction means that the heat, the positive Q, the heat is being absorbed into the system. That means that the energy flow is going into the system. We can say that the energy inside the system is now increasing. And that's a really big deal, that the energy inside the system is increasing. On the other hand, you have exothermic, and exothermic means that now that the heat is being lost in the system, or it's being released by the system. That means that the energy flow is moving out of the system, which means that the system is actually seeing a decrease in the energy. Hopefully this helped you get a basic understanding of thermochemistry, and helps you understand the law of conservation of energy a little bit better, as far as understanding heat and understanding how energy can flow in and out of the system.